Hi, everyone. I'm building an electric car from scratch using Rust. But I want to make sure that I set expectations right away. There's no finished sports cars that's going to be driving out from behind the curtain or anything like that today. This is a very early stage of a long and very ambitious journey. And frankly, success is not the most likely outcome. I'm not a car guy. I have no background in mechanical engineering, machining, hardware, power electronics. So by now you're probably wondering, what am I doing in this room? Maybe there's still I could catch the talk on the other track. I do have more than a few years of software engineering experience, and as I'll talk to you during this talk, or as I'll mention during this talk, I think that could be very, very applicable, because Rust may be key to an interesting approach to building automotive solutions that, frankly, no one's exploring today. So with that, my name is Brad Gibson. You'll see me online on technical forums as U007D, pronounced Curly if you want to know the trivia there. And welcome to my talk, Rusty New Rs. Look ma, no C added. Many years ago, I saw a documentary, and I thought, dude's making sense. If you have seen Inconvenient Truth, I thought it was a powerful documentary, and it was motivating. And at the end of the documentary, it's a documentary about climate change and our role in it. And at the end, there was a section dedicated to what can I do about it. And the advice was to write your political representative. I don't know about you. I don't know, whether you consider your political representatives to be, very responsive to your needs or not. But I just didn't feel that was going to get the job done. And I thought, crap. There's like a 1% of a 1% chance that I might be able to move the needle just a tiny bit with what I know, and perhaps leave the world a little bit better than I found it. So that started this journey. Many years ago, I also attended a CPP-Con. I'm an old C++ and C programmer. And Bjarne Stroustrup, the creator of C++, gave a keynote there. And we had just seen great success with C++11, and there was all this energy and revitalization, and C++14 had come out, and it was kind of disappointing. We didn't get all the things that we were excited about. And then there was a talk like, the next one, C++17, is going to be great. We're going to be back to that C++11 high water. And he had a list of 11 major features that were coming, and that would make the language easier to use and more safe and all these good things. And he said he didn't see a reason why we couldn't get all of these. I thought, that's great. Happened that same day at lunch, we were both waiting for our respective parties to go to lunch. And he and I are just standing there, and it's Bjarne. So of course I, introduced myself, and we talked for a few moments. After getting an understanding of where things were with him, I just didn't come away with the feeling that C++ as a language overall, not Bjarne, but the overall committee, was going to drive in the direction of safety with the same level of, with the same priority, right, that I had. So it wasn't that it didn't matter, it just wasn't that the same priority. And I think history since then has largely borne that observation out. But that was when I discovered Rust in late 2014, early 2015. It was shortly thereafter, Mozilla had some well-publicized challenges around changes in Firefox, and this is a famous photo for many of you. Creating safety in a very complex environment was incredibly difficult. They had some of the best C++ programmers in the world. Firefox is written in C++. They rewrote, big parts of the language in C++, and they ended up exactly where they started, roughly speaking. I mean, there may be Mozillans in the room who were part of this, so I'm not speaking authoritatively, but this is sort of the effort that went in. And when they realized the challenge that they were up against, this is sort of Rust's origin story, when it broke out from being Graydon's side project to being sort of the language that we know and love today. So what's this experiment about? The experiment is, can I make a fun, fast, beautiful prototype electric vehicle in an effort to learn what it takes, but it's got to move the heart and soul? Can one guy do that in his garage? Is it possible? So the experiment is asking a number of questions. Is it possible to build a compelling car? This is where it's not just a technological achievement from a mental perspective. It's actually emotionally compelling. And can I do that? Is it possible to do that in a sustainable way? Back to the inconvenient truth. Can this be done in pure Rust? No C added. Furthermore, can this be done from first principles? I understand there's many people from the automotive industry at the conference today. I don't know if any of them are here in this room, but there are plenty of software-defined vehicle initiatives that are going on right now in the automotive industry. And if you were to do, say, a Google search on what engineers think about AUTOSAR when they're away from, when they can speak their minds freely, it's not pretty. And so a lot of those initiatives are certainly well-intentioned and well-meaning, but it's interesting that the people implementing, underneath them are, profoundly unhappy, and it's not something that most people enjoy working with. And I think Rust has an opportunity to change that. As I said earlier, is it possible, I'm not a car guy, so is this possible to do as somebody who's not a car guy? I did not grow up, turning wrenches. Grew up with the Commodore 64, which is a little bit different. What would happen if we took every possible problem and turned it into a software problem? Now, for those of you like me who are not car people, per se, I'll give you an example of what that means. All the cars that we own today have a part in them. It's called a differential. And what it does is it allows the wheels on either side of the car to turn at different rates. Well, why would we want that? Well, if you imagine a car turning a corner, that car, the inside wheels, have a shorter arc to travel than the outside wheels, which is a much longer arc. Of course, the car has to stay together through the turn. So given that the two sides of the car are traveling different distances in the same period of time, it must be the case that the wheels on the outside and the wheels on the inside are turning at a different rate. And you can get an open differential and a limited slip differential, and you can get all these different parts, but I can tell you this. They all weigh something. They all cost something. They all wear out. Best part is no part. Now, in an electric vehicle where you're using one motor per wheel, this entire issue becomes a software problem. If the software knows how wide the car is, and based on the driver's steering input, you know that the angle of the curve that you're going to be taking, you can make the calculations that you need in order to turn the wheels at exactly the same rate that the differential would turn them. But there's no differential, there's no weight, there's no cost, there's no range, there's no loss of range because you're not carrying any extra equipment, and there's no maintenance, nothing to break. Now this can be extended far further than this one part, but that's an example of what I mean by taking a problem, taking an existing part that might not even be seen as a problem, and turning that into software. There's plenty of applications for handling to do the same thing, as well as parts reduction for reliability. Could this project become the foundation of a company that that instead of just valuing profit, balances benefits to people, planet, and profit? Now that's a relatively new type of organization called a B Corp, or a benefit corporation. And I think that has a lot of ethical ramifications. And last but not least, how can these goals be made compatible with an open source project? Rust, GCC, LLVM, they've all given us so much. Our entire careers, frankly, my entire career is really a testament to open source and the benefits that we've gained from it. It would be great to be able to give back. So that's what this experiment is about exploring. I don't have a ton of answers for you. I can share with you my learnings along the way. So this is the anatomy of our talk. That was the intro. Working now on prototype one, this is now a history talk about how I got through delivering prototype one. The goal of prototype one was to build a battery pack from scratch and to learn what was required to make that work. See if I can get this right. All right, so what I did is I convinced my wife we could move the cars out of the garage, resurfaced the ground, epoxied everything, ran some wiring, and turned it into a workshop. I've never done machining before, as I mentioned, so purchasing equipment, learning how to use it, deciding what to buy. I have additive and subtractive manufacturing, prosumer level additive subtractive manufacturing equipment in the form of a 3D printer and a CNC machine set up in there. A bunch of things, welding system, taught myself how to weld. Thank you, YouTube. We're really in a golden age of learning. And it's possible to have somebody with 45 years of experience welding pipes just give you every trick of the trade that they knew because they love it and they're sharing it with the whole world online. And it's fantastic. So as I said, prototype one was about building the battery pack. So I sourced about 200 1865 cells. They're the high energy cells that you find in a Tesla Plaid, and learned how to put them together as a pack. It's not as simple as just parallel this and series that. Every cell has a different internal resistance that has a different capacity. You need to combine your cells in the right way in order to make sure that the modules have roughly equal capabilities, both in current and energy capability. Assembling it, you can't damage the cells, so you have to do certain types of spot welding. I wanted it to be safe because I knew my kids were going to play with this vehicle, so I didn't want it to catch fire. So each cell is individually fused. I had to learn all of this from scratch. And the battery charging equipment you see in the upper right corner, I do have a pointer here, over here in the upper left corner of the screen is something I also had to build myself. And something as simple as powering that via a USB-C cable meant I had to learn all about USB-C standards for delivering power through the cable. No data, just power. And it's not as simple as you might think. But it's fantastic. It was great learning. What ended up happening? I wanted a custom chassis. I thought I was going to build this car that was going to be amazing. And my son said, "No, Dad, you said battery." He's 15. He was 14 at the time. He says, "No, Dad, you said battery." So he said, "My friend has 2 kids' go-kart chassis rusting in his yard that they haven't used for 2 years. I'm going to go get one." I said, "No, I don't want any more junk. I want to build the chassis." He says, "No, Dad, I'm going," and he's out the door. Half an hour later, he's back, and he's got this thing, and it's full of dirt and garbage, and it turns out he was 100% right. I had to stay focused on the problem, which is the battery pack. So we cleared everything off the go-kart. I put on a store-bought motor, chain drive, and hooked up the battery pack, which is a little hard to see in this photograph, but it's the big black box. And on top of that is a store-bought battery management system, so you can keep all the different modules in the battery pack equalized, and the kids just love it. Here's my son in low power mode doing one-handed drifts. My daughter trying to do the same thing, and if anybody ever wanted to know why women live longer than men, there it is, right there. All right, so that's the history. That's where we were with prototype 1. I put that on the road last year. The kids from the neighborhood all came over. That particular prototype, even though in the video it didn't show that, it does 64 kilometers an hour, which is about 40 miles an hour. And it is obviously a kid's toy. So at that speed, it's vibrating. And it'll actually vibrate so violently that the gel in your eyes will shake. And so you literally can't see. You're blinking, trying to clear your vision. It will not clear. It's a hoot to drive that thing. All right, so where are we now? Today, I'm building prototype 2. Prototype 2 will be a full-size 2-seater vehicle. In fact, it's going to be a replica of the car you saw at the title slide of this. So to do that, I have purchased a 3D scan of the body. It's a 1955 Mercedes-Benz 300 SLR Uhlenhaut. I did not know the car existed. How we chose it was that my son, his friend, and I sat down and we picked 5 cars we thought were nice, and we all voted. And this car made it to the top of the list, just barely, because you can imagine what teenage boys want, like Fast and Furious style bling. And so this is what we ended up doing. So I've got this 3D model is not mine. This is the state of my 3D printing to print the pattern. So what ends up happening is you 3D print a pattern, which looks just like a body, like this. Then you cover it in fiberglass, which turns it into a mold. And then you do it again, and then the mold will let you build a car body out of that. And so you have to do the whole thing basically 3 times. But then you can actually make a second body because my son swears he wants one too. All right, so this is RustConf. So let's talk about some software. So first of all, the software side of this project, for prototype 2, the goal here is to implement drive-by-wire. This means there's no mechanical connection between the steering wheel, the wheels, the brakes, the accelerator. It's all done with software. Pure Rust, no stud, all the usual suspects. The project is cross-platform in the sense that it runs on ARM, it runs on RISC-V, it runs 32-bit architecture or 64-bit architecture, microcontrollers or CPUs. And the key here is that, and I'll encourage anybody who's doing a project like this, the key here is to invest in yourself when you begin. The build, like for anyone who having done embedded systems work, the command line to invoke an embedded build can be multiple hundreds of characters long. And if you need to have all this arcane knowledge in your head, it can be very easy to get into a state where you're the only one who knows how to build. But the first thing I did was invest in the build system to make sure that the build system knew everything there was to know about it, and I simply specify the board and the memory maps and everything else that needs to be built, and the way it needs to be built. And the variations of the different boards is all contained within the build system. And it was a fairly heavy investment up front, but now I am so glad I made the investment. From the software side, it's loosely coupled, so I'm using ports and adapters, also known as hexagonal architecture, which is not often seen more in enterprise applications rather than in embedded systems projects. Doing BDD testing is actually quite difficult in hardware world because you need hardware in the loop and so on. So I'm actually learning that area and figuring out how to do that best. I'd like most number of unit tests to run possible on my laptop, and then there's some subset, a larger set will run as unit tests on the device, and then there's a larger set still that will be in integration tests and system tests and so on. Using domain-driven design, which is one of the most complicated parts of this project, the constraints of the hardware underneath are not matching neatly to the constraints of how I want to look and think about the software. So building a type state-based system where these two mesh seamlessly is by far the biggest challenge to date. What's interesting is that hardware is notoriously difficult to track in terms of understanding its state. But this is really the architecture of how the system is put together. We've got some hardware down here. We have something called a peripheral access crate, which is really software representation of the hardware at this level. And then there's a level above this, which you can see here that is broken up, called a HAL, which is a hardware abstraction layer, which is, you could think of it as, when you make a recipe, you don't start baking bread with atoms, right? What you do is you use flour and milk and other things. So you can think of the HAL as sort of putting together the base components of the hardware that's available to you on chip. So that way you can be working with more useful components. You're not starting down from the atoms. What's really interesting about this, and credit to Jorge Aparicio for the embedded HAL crate, and frankly to, I can't pronounce Dario's last name, but the author of the Embassy crate for building on top of that and adding async to it, really does make this manageable, easy, and most importantly, type safe. So what's happening here is that hardware is not type safe. It's very dangerous and difficult to control correctly. But the pack, the peripheral access crate on top of it builds a type-stated abstraction. And on top of that, we have the HAL and, of course, my software, which I'm also working to make type-stated as well. So in the bad old days, what you would do is you would simply get the data sheet, which is approximately 1,400 pages long. You would put it all together and basically name an address, name an address, name an address. And if you needed to write a value to a particular field, you would, I have to write to this field, but not, not any of the bits around it. You would shift your bits in, you would mask it, you would read it, you would write it back. It was, you get one number, an off by one error would be pretty catastrophic. This example is a real example. 75% of the code is not here to make it run. Today, under Embassy and using embedded HAL, other than the imports required to make this work, this is everything that you need to do. This is also type stated. So in the case here, I'm using something called an analog to digital converter. I'm taking a voltage and turning it into a digital value. Whatever pin I happen to use, in this case, here's an example with pin 27. This is an example lifted right from the Embassy crate. I'm using pin 27. If pin 27 is not hardware connected to the analog to digital converter on the board, this will not compile. So it's not possible to get spurious readings because you're reading some other device that you didn't know you were that was hooked up to the pin. This is not, if it's not an analog to digital converter pin, it's not going to work. Okay? This is the power of type state, and it's really, really important when you're building complexity. You can depend on those abstractions. So to save a bit of time here, I'm going to talk, very briefly. But one of the things I did is I configured the clock on here to count clock cycles rather than to count milliseconds. And so with the tool, with that precision, I was able to go and measure everything. And I can see things like compiler optimizations that get elided because I changed the code in some way, right, in an unexpected way. I can measure the latency of async versus hardware interrupts. This particular chip has both a RISC-V mode, both an ARM mode and a RISC-V mode on the same silicon. So you can compare efficiency between the two architectures for what you're trying to do. So it's really, really powerful, and lots of data is going to be coming from this particular way of measuring. But right now, I can tell you that I can read a 64-bit value out of registers in exactly 6 clock cycles. So there's lots of things you can measure. I think I just mentioned a few of them in terms of what's going on. One quick anecdote here is that by using this Raspberry Pi Pico in default mode, what it did is it pushed all of my code into flash memory. There's 2 megabytes of it on this little microcontroller board. It's a $7 board. And it ran the code from flash memory. And flash memory is fairly slow. I was wondering why it was 140 clock cycles to read, to read a value from a register. And it turned out, thanks credit to James Munns, who actually tipped me off on what might be the problem. This XIP feature is called execute in place. It's a convenience feature. But when I moved the code into static RAM rather than flash RAM, the code ran 15 times faster. So I began to wonder how many systems are out there in the world that are set up in default mode running 15 times slower than they need to be. How many times did we buy 15 times the hardware capability that we needed because we didn't know about this? Okay? This is the very first thing, right, that cycle clock counter told me. It's like something's off, and we found it, and it got a 15x increase. All right, so we've got some interesting things about reading the analog to digital converter. When we think of a steering wheel position, providing a particular voltage into a system. What we have here is an analog to digital converter. There are a lot of channels, so you can imagine the steering wheel's on this channel, and the accelerator's on this channel, and the brakes are on this channel. Well, what happens if the channel you're reading isn't the channel you think you're reading? So what the person's doing with their accelerator, you're mapping that to the steering. Okay, what happens if that occurs because you ask the analog to digital converter to iterate, and the analog to digital converter, somehow you and the converter get out of sync? This could be disastrous, right? Loss of life level disaster, unthinkable. So this code needs to be written in such a way that that cannot happen. And that's where type state comes into play. Some of you may be familiar with new types as an abstraction, but type state goes even further to ensure that it's just simply not possible to get that hooked up wrong in software. Your software and your hardware teams still have to talk, right? Which line is the steering wheel on? You've got to make sure you get that right. But once you've got that set in exactly one place in your software, it won't compile if anybody gets that wrong, regardless of where they are in the software stack. I'm going to skip over, but it turns out that inside this ADC, there's something called a successive approximation register controller, and it actually puts this thing called a conv error. And I saw that, and I said, uh-oh, you mean my conversion might fail? When you're trying to steer or step on the brakes, the hardware might say, I'm not sure what's happening. Turns out the answer is yes. And so you need to think about that and how we handle that in software. So there's a lot about safety here that I'm skipping over for brevity, but this is really important to keep in mind. Okay. So let's, moving forward, I'm building this prototype. I haven't talked about chassis and suspensions, but as I said, it will be, full size, and we're building this. But from a software perspective, the software is unaware of the size or the power of the hardware. So let me begin with a demo for you. And what I'm showing you here is a top view of the hardware I have on this table. This black knob represents the steering wheel position. Obviously, in reality, you could have this value encoded in any number of ways. But this red one is your brake position, and this one here on the right is your accelerator position. So our first demo will be to run this code that I've been talking about. You can see that oh, no, you can't see. Is it not sharing my screen? Oh, I know what's going on. Okay, so you can see that I compiled the program, I ran the program, and by running the program, I actually sent it from my laptop over to the Raspberry Pi Pico over here. It's in Flash and SRAM, and then it's running. And so you can see there's values down here on the bottom. And if I take my steering wheel angle and I change it, you should be decreasing down to -1, and then it should increase all the way up to +1, which is interesting because I can only see it down here. Yeah. So we go down to -1, +1. And if I leave that there and I turn on my accelerator, you can see that the accelerator position is at full 1, goes down to 0. And what's really interesting is that I can leave my accelerator, say, at 3/4-ish, and then I'll apply some brake. So now I'm increasing the brake field, and you can see here that nothing's happening to the accelerator. The numbers are jiggling because there's noise in the analog world, and I haven't done any filtering whatsoever on the values I'm getting from my analog to digital converter. But you can see here that the brake doesn't change the accelerator value at all. Okay, so that's the software working. Largely type-stated. I have a little bit more work to do, but from the hardware on the way up, all the way up. I have a second demo for you, if I can. Okay. So for the second demo, what I'd like to do is I would like to take those inputs and actually apply them to a vehicle. Now the plan was talking about heart and having designs that actually are compelling. The plan was to show it to you in something that actually looks like the car I'm trying to build. But it turns out that my 3D printer made this solid, and so it's going to be really hard to cram this in when it's solid. I thought about dremeling it out, and then I just said, I'll just print a hollow one. And when you print a hollow one, because there are parts of this project, like you can see these motors here, they are screwed in. I have to screw them into the side of this, so I had to make the 3mm walls solid, and it takes forever. It's actually going to finish about 3 o'clock today, just after we could use it. So unfortunately, I have to give you the science experiment version, right, of this. And all that we have on here are these two motors. a couple of 1865 batteries running around 7 to 8 volts. And there is steering capability, but I also have a part just showed up this morning from Amazon, which is called a buck converter, that will take the voltage down into the range I need it to not burn out the steering motor. And so I wasn't able to get it working this morning for you. But we can still get it going because we have our throttle position working just fine. So with the same software, I flip back to still running. So what I'll do first is I will put the batteries in, all the way in. So my motor control, you can see, is giving me a red light, which is telling me it's going to take a signal. And if it gets between 0 and 3 volts, and if it gets, say, half that range, it's going to take from its source, which is the 8-volt source, or if it was a larger vehicle, it would be an 800-volt source. And it's going to give you about half the power, half the voltage, half the current from that source. So all it's doing is it's giving you proportional control without drawing the actual power from your little tiny board. That's how the concept works. Now, I don't want to do this while it's actually on the table, because it will drive off the table. But here I go with accelerator. Yay. Okay. So here we have software. So you saw before when I added brake, it didn't change the accelerator value. You can still see it's on the screen right there. So I'm going to leave the accelerator where it is, and I'm going to add brake. Okay? So what you can do with software is you can map all the things you want to do. You can say, I want my accelerator to have really fine control for the first part of it, and then later when I'm almost near the floor, I want it to be really strong, or I want my brakes to work in a certain way. Once you put your controls into the software domain, your imagination is really the limit for what you can do. So thankfully, all my wires held together just long enough to do the demo. All right. Okay, so that's the demo. Fearless, I have to remember his name now. Last year at RustConf, Joshua Lebo-Fieser gave a fantastic talk about the importance of extending type safety beyond basic memory safety, basic concurrency, and into, I'm sorry guys, there we go. Gave a talk beyond basic memory safety and basic concurrency to extending into, in his case, a network stack, in my case, an automobile. So I think this fearless whatever safety, it's hardware safety provided by Embedded HAL. It is fantastic. It's really important. It can help. Building reliable correctness-first software is absolutely critical in cases like automotive and aerospace and things like this. And I think Rust can take this from being something that engineers hate and turn it into something that engineers love. And I think that's going to do more to change the face of safety in technology than anything else. It's just having the people who are working on it actually enjoy using it. I skipped my bio. I'll show you a QR code about me in a minute. You can find my LinkedIn, my GitHub. You can find me on Discord and Reddit and other places. But I guess the one thing I will say here is that I do lead the Seattle Rust user group. So anyone who is interested in Rust, and if you're in the area, happy to have you come out. It's entirely free, and you can find the Seattle Rust user group on meetup.com. And if you liked what you saw and you thought this was interesting, please contact me with your comments, thoughts, or your questions. Obviously, I love talking about this topic. That's a wrap. Thank you. I don't know how much time I have. Do I have any time? Okay. So time for one question. Make it a good one, I guess. I'll repeat the question.
Yeah. So
Fantastic question. The question was, when you're dealing with type-safe idioms or type-driven design, you often have a situation where hardware does not want to allow use of the thing in the way that you need to use it. So you often have to take the thing you have and break it up into a bunch of other things that you didn't need, but the system wants you to do it. And then you're juggling a lot of mess just for the privilege of working in type state. This is a problem with the analog to digital controller. You saw all those different lines coming in to the one analog to digital controller. And so whenever you talk to a channel, guess what? It takes a mutable reference to an analog to digital controller. Well, which one? The only one on the board. But I got to have a mutable reference to it, which means none of the other channels can even hold a reference to it. It's exactly that problem. Are there good ways to handle it? Maybe. I am still looking for that. I actually have an approach, right, that I'm working on with this. I haven't finished it yet, so I can't vet it for you, but that is actually top of mind. And I do think we will get to a place where this is good. So reach out to me. I will be happy to keep you up to date on that. And frankly, we could probably co-develop a pattern. Be happy to do that. All right, that's it. Thank you, everyone.